So hello everyone, thank you for coming. It's actually really interesting to see so many people in the room who have got a passion for TLS. Normally we don't see this many people interested. So today I'm going to talk about TLS fingerprints and how we can compare them to be a little bit more effective in the threat hunting domain. So a little bit about who I am first. I'm actually a recent cybersecurity graduate. I came to kind of cyber a little bit late in my career. I'm currently employed full-time as a generic application developer, full stack, mobile, that kind of stuff. Got a broad interest in threat hunting, as you can probably guess, malware analysis, basically any kind of future web trends and technology. So I'm going to kind of launch straight into this here. And I'm going to introduce the topic of similarity to you, but I'm going to introduce it with a little bit of a twist. So we know already that in the domain of cybersecurity, similarity is used pretty extensively already, but we mainly think about it when we're thinking about malware and malware analysis. But I don't want to talk about its application to malware specifically. I actually want to talk about its application in another domain entirely, and that's chemistry. I know it's a bit of a weird thing to pull together, but I'm going to give you an example of how we can use that influence to kind of push back our perimeter a little bit and how we can use it to help us identify tools and domains that serve malware before we even have to worry about the malware itself. So firstly, I just want to give a little brief overview of what I mean by similarity in this context. So we've got two different kinds of hashing there that we do on files. We've got cryptographic hashing at the top, and we've got fuzzy hashing at the bottom, which is probably what most of us are more familiar with. And all I mean by similarity is when you're trying to compare two files and they're not quite exact, they're slightly different. But actually how we establish that level of difference is a really hard problem to solve. So the most commonly used approach, which is used by antivirus, that kind of thing, is when it's called fuzzy hashing. And when they break down a file into multiple smaller files, hash them and compare them to one another. And they do that to get around obfuscation, small changes in malware files. It's actually really, really effective. So we know we can make use of similarity when we're looking at malware, and we know what TLS is. I guess how do we bring them together and why is it useful to do that? But firstly, I'm going to explain why I'm focusing on TLS at all. So when we look at C2 servers, phishing sites, malware domains, we can fingerprint what we can see really, really easily. We can fingerprint the content, the headers, the frameworks, those kinds of things, favicons, all really easy to do. But the TLS gives us something a little bit more subtle, and it allows us to fingerprint something that we can't see. So some of the extensions, for example, can give us a really good insight into that underlying operating system. And a good example of that is the extended master secret. So if you're looking at the TLS of a server and it supports extended master secret, you know for definite that it's going to be using OpenSSL 1.0.1 or more. So it's actually a really subtle approach for profiling servers that's genuinely quite effective. So here I've got a very, very simplified version of the TLS handshake. So forgive me, it's very, very simplified, but I'm going to talk to you a little bit about the fingerprinting process. And we're going to introduce a system called a JARM. I don't know if anyone's heard of it, but it's used quite commonly in Showdown, VirusTotal, those kinds of tools. And all it is it's a script provided by Salesforce that you can run against a server. And it will send 10 curated client hellos. And from that, you will get 10 specific server responses back. And it amalgamates those, hashes them, and gives you that little fingerprint that you can use to find similar configurations out in the wild. So why is similarity useful for TLS fingerprinting? It's a really interesting question, because exactly the same problems for malware exist with fingerprinting. Threat actors can make tiny, tiny configuration changes to their servers to get around known fingerprints. So having a fixed hash approach is fallible. But it's also incredibly useful because more and more commonly threat actors are using automation, they're using common technology stacks. So if we look at things through the lens of similarity, rather than those exact fixed hashes, it allows us to kind of broaden our horizons a little bit and find similar servers. And this is the big question. If both of these things are so useful, why aren't we already doing it? And actually, it's because it's genuinely a really hard problem to solve. Because unlike files that are quite static, we have traffic. So there's a whole bunch of things that any TLS similarity mapping would need to do well to be effective. Mainly, those, the negotiation parameters are complex. So it would have to handle all of those. Also, it would have to handle huge volumes of nodes, domains, servers. But the most important bit for me was that it has to provide meaningful graduations of similarity. We all know about clustering. There's a whole bunch of AI work that you can do around clustering, but generally they're too broad. There's too much collateral involved in clustering attempts. But also we can't exclude any element of the TLS connection because we've only got a finite things we can look at. So we spend a lot of time looking at this problem, but what if another domain had already solved it? So I'm going to introduce to you something from the chemistry domain. It doesn't look great on there. There's some detail that's been lost, but TMAP is a Python library for mapping chemical modules. So it really hones in on fine-grained similarity of these modules, but more interestingly, it can handle data sets in the billions, and it retains those nearest neighbor relationships really, really well. So this image is the natural product atlas. And all that is a database of natural products derived from microbes, coloured by their origin. So the little inset you have here is similar compounds grouped by their family, genus, fungi or plants. So you can see those similarity patterns there. This one is the same approach, but 6,000 servers scanned and plotted by just their TLS configurations. So in this one, we've got red nodes are obviously the known malicious domains. We've got amber nodes, which are newly registered domains within the last 2 weeks. And the green ones are the known good domains. So you can already see just from that there's, even though these cryptographic fingerprints are very different, that there is some trends in the way these malware and phishing domains are actually using their server stacks. So I'm going to give a really high level of how this works. So all I've done is take the JARM tool, run it against a whole bunch of servers on the internet, but instead of hashing those fingerprints, we create binary vectors from that output. And that means there's a post-processing step where we take every TLS extension that we've seen across the entire set of domains that we've scanned. We create these column headers, and then we plot against them what we have seen and what we haven't seen. So the bottom here is the basis of how the visualization you've just seen works. So this is a local sensitivity hashing forest. And if we walk through the Google domain here, you'll see we go right at the red node, right again at the green node, and then right at the final blue node. So it puts our domain right in that far bucket. We do the same with the malware one, and we'll go right at the first node, left at the green node, and then left at the blue node. So we can see it's in the fifth bucket. So instinctively, just by where it is in that forest, you can tell that they have something in common. They're not entirely different. And basically, this just demonstrates how you can see the more they have in common, the closer they are in those buckets. And if they're identical, they're in the same bucket. So what's the outcome of this? So it gives us actually a really fast and efficient method to compare TLS fingerprints that we don't normally attempt to do. So the image here is actually a mixture of technologies, and this scan was entirely incidental. We've got a mixture of technology stacks. So we've got GoFish in yellow, we've got Metasploit in pink, we've got Burp Collaborator in blue, and we've got some tactical ROM in there as well. So we can see from this demonstration that the tech stacks do align, even though these are specific, like the cryptographic hashes are different. But the technology themselves have limited variation in how their configurations are rolled out. So it's actually really, really useful for classifying servers as well. So where next with this? So TLS in itself is becoming a little bit less useful as tech stack hosting is changing. So one way we can move this forward is we can enrich the vectors. And that's all I've done here. I've added in just a couple on the end to demonstrate how we can incorporate some HTTP header data. So this is really, really effective when TLS similarity is super high. And we see that in CDNs. So CDNs are interesting because you naturally get more overlap with good TLS fingerprints to bad ones because there's limited TLS configurations you can do on a lot of CDNs. They do restrict the kind of cipher suites and the versions of TLS you can use. So this is a data set. Everything's hosted on Cloudflare, and you can see genuinely it's pretty pointless. This is just TLS on its own. You've got red domains scattered in with good domains, so there's not a lot of trend analysis we can do on this one. This is the same data set with the incorporation of that HTTP header data. So you can already see that those malicious nodes are grouped tighter together. They clearly do have a lot in common when we introduce the HTTP header data, and the technique becomes a little bit more effective. But also, it's not limited to just being HTTP header data. Like, you can take this a really long way. And in some tests and some analysis, like, I introduced certificate data, whether it's self-signed certs, those kinds of things. But also the HTML tags, do analysis on like the first 50 tags. The format of the website itself, you can really introduce a lot to this because TMAP can handle up to billions-sized vectors really, really well and really fast. So there's a lot of possibilities here. So I guess wrapping it up, my main point for bringing this here today is to try and encourage people to look a little bit more out of their domain. So, a lot of the problems we have already been solved. We could just look a little bit more outside our own boundaries. But also, this is genuinely a really useful technique that you can employ for threat hunting or monitoring your own domains. Thank you very much. I actually just want to say a big thanks to my mentor, who's been excellent, Matt. And yeah, thanks for listening. I hope you learned something. And if you've got any questions, I'm here for the rest of the day.
Thanks, Amanda. We do have some time for some questions, if anyone would like to ask some.
Damn it.
Hey there.
Hi. Congratulations for the presentation. I have a question. Is this only working for printing? Or can it be used, for example, in iris or any other biological?
Anything. If you can put it in a vector, you can use this technique.
Okay, thank you.
I saw another hand up, I think. Yes. Over there.
Yeah, my question was, so building that kind of vector store, or the graph that you got there, that's a kind of a point in time build.
Yep.
Have you looked at any ways to kind of keep that going, like just as like a streaming engine of new domains as they come in and new enrichments going?
Not yet.
Okay.
But I think it would be doable.
And then the other question was on that the last one of the last shots you had where the malicious domains were clustered in the top. That required initial identification of at least one or two of those domains as malicious before you would know that cluster was malicious.
Yeah,
Okay.
absolutely.
Right.
So, yeah, if you've got a seed domain, you instantly know if you've got like 5 or 6 clean domains around it that you should be looking at those.
Okay.
But you do need...
You need something classified.
Yeah,
as
absolutely, because otherwise they're just unknown.
Yeah, we've got time for one more. There's a chap there. Oh.
Will this work for quick as well?
Yeah. Yep, genuinely, yeah. This is just packet data. That's all it is. So it's pulled out of the packets.
Fabulous. Thank you so much, Amanda. That was awesome. And yeah.